All right, people. Hope you're doing okay. Hope this isn't too boring for you. Sports offer a lot of opportunity. Politics offer a lot of opportunity to sort of test things. You'll see a science one after this. If you haven't done the Mendel's P problem, which I think it comes up in our high school science classes at MMU. There's discussion of that same guy. So, if you ever watch the Patriots with Bill Belichick, he very often doesn't want the kickoff in the first half, which most teams want that. There are even some coaches who don't want the kickoff received in overtime, which sounds crazy to a lot of people. If you look at the statistics here, between 1974 and 2009, coaches use a ton of analytics nowadays, and they have little math nerds following around giving them information. The whole movie Moneyball is about that, about statistics and making better decisions and informed decisions based on analytics. So, as you dig through this, you definitely want to read into this. 240 out of 428 games were won in overtime when they won the coin flip. So that's your sample proportion. Sometimes you have to calculate that. It's not just handed to you. Think if you divide those, again, my hat's a little crooked here. Sorry about that. You can put the hat straight on your paper. I think that's around 56% of the time. So they won more than half. 44% chance of losing in those situations, and based on those, pretty long span of data. So hopefully you jumped in and defined some hypotheses. Again, it's a football game, so there's theoretically a 50-50 chance of winning. If nothing's going on, either team should win. They made it to overtime. They're tied at overtime. There could be a 50-50 chance of winning. The alternative would be, we think there's, by winning the coin toss, you have a greater than 50% chance of winning. Clearly, it's a little bit bigger, 6% bigger than that. So then we dive in and calculate that Z. So we said this is 6% difference on there. That's the top of the numerator of your Z calculation. Hopefully I did this stuff right. Using that null proportion, 0.5 times 0.5, divided it by my sample size, which was 428 in this case. Take the square root, and hopefully that's looks like it's right. And I got a Z statistic of 2.5. And again, just to refresh your memory, we can use that table symmetrically, or you can use the positive side of the table, but you want to get a tail on there. And if you go down to 2.5, I'm using the negative side in this case, but it still represents the same thing. I don't have to go far. Right there should tell me that's a really small p-value, 0.0062. On a 1% level, that's significant. There's a less than a 1% chance of this many games being won with a pretty large sample size if it's a 50-50 chance of winning. Here's a 50-50 chance of winning. We're far enough away from that. We're 2.5 standard deviations away from 50-50 chance. That looks pretty significant. Less than a 1% chance of that happening if the coin toss doesn't really matter. So it looks like this data definitely suggests the coin toss is an advantage. Bill Belichick should be receiving that ball in the kickoff in overtime. He can still choose what he wants to do first half. Obviously the Giants, doesn't really matter what they do for the kickoff. They're in trouble. Good science example at the end of this. This is Gregor Mendel. Did a lot of genetic experiments. In this case, looking at pea plants and trying to figure out whether the pea plants are smooth. I don't know why anybody cares, but smooth or not smooth. Apparently that's an important thing for genetics and, fruit. This is a fruit, not a vegetable. Keep that in mind. That's exactly how my daughter eats them. She picks them out and eats the peas out of there and then eats the covers later on. So, first thing you want to think about is that sample proportion. And this is where reading is important. Hopefully you read through this more than one time. The sample proportion was not 3 out of 16, 108 out of the 556 plants, which I think is 0.194, which is very close to 3/16. The 3/16 comes into play for your hypotheses. Mendel is trying to decide, is this sample supporting or denying the idea that 3 out of 16, he has this genetic theory that 3/16 of the plants will be smooth. And if you calculate that as a decimal, I believe that's 0.1875. So there's your null. The alternative, if I read this carefully on here, says it's just going to be different. Doesn't say greater, doesn't say less, just says different. That means not equal to 0.1875, which, just a preview here, spoiler, that means it's a two-tail test. Could be on that extreme or that extreme, tail. We want to double our p-value at the end of this. So hopefully you're able to calculate z. If you didn't already try it, pause and try to calculate z. And you'll find these proportions are very close. So Mendel's sitting there going, wow, those are really close together. They're, less than 1% apart in terms of percentages. I think I did my standard error calculation correctly, 0.0166 roughly. It depends on when you round in this problem. You might get something a little different. But your z statistic won't be that much different than 0.4. Which hopefully, as soon as you see that, you go, that's not very significant. You know that 0.4 is close to the null. That's not even one standard deviation away. That's not even half a standard deviation away from the null, from the middle. But your math teacher still would want you to find a p-value. So you go into 0.4, move over one column, and I think it's around 34%, 0.34. But just to remind you, we're not going to use 0.34 for our p-value. We're going to use 0.68 because we've got to double. We've got to consider this tail, or it could be this tail. So we've got to consider both extremes on there, which is why we double that p-value. Either way, whether you use 0.34 or 0.68, it's not significant. And in fact, Mendel's idea, because he was trying to test if it is 3/16, is supported. It appears his idea of it being 3/16 is pretty close. This was pretty close to 3/16, kind of makes sense. With a good enough sample size, his standard error wasn't that small. Limited amount of error. Good job, Mendel. You're a smart guy. So hopefully this helps you attack some homework problems. Hopefully you're not quick enough to see those answers. If you want to check them, you certainly can. Hopefully things are going okay. We'll see you. We'll see you down the road, USA.